Dr. D. Okay, here we go. Work. All right. This is basically physics, but remember, in this class, we derive physics. We don't simply take formula that's for babies and use that. We derive our own formula. So, we know in physics that force equals mass times acceleration. Now, acceleration is the second derivative of displacement with respect to time. So we really have mass times acceleration here. So now work is a force times a distance. Now I want to make sure that you understand we've got units from the good old USA. And then we've got units from France. Let me demonstrate. Right here, we have a 25-pound weight. Now, if I take this 25-pound weight and I pick it up from the ground and I lift it 7 feet high, how much work have I done? Well, work equals force times distance. What was the force? 25 pounds. What was the distance? 7 feet. So here's how you do it in the USA. You say the work was 25 pounds times 7 feet. And you get 25 times 7, which is 175. What are the units? Foot-pounds. Simple. Force times distance equals work, and work in the USA is foot-pounds. Piece of cake. All right. Let's say we're in France, and we have this same dilemma. Well, work still equals force times distance in France, but in France, they know nothing of the pound. So we have to take our pound and convert it. 1 pound equals 0.453592 kilograms. All right, so our work is going to equal $11.3398. Did I do that right? I better check this out. I may have screwed up. So we have 25 pounds times 0.453592. That's 11.3398 kilograms. Now, kilograms is not force, though. Kilograms is mass. So what we have to do is we have to convert this mass into force, because we're in France. So the force unit is a really strange unit called newtons. So they have 9.81 newtons for every kilogram. So now we have 111.243438 newtons. Now, we have to multiply by the distance. Now, the distance, 7 feet, because we know that each inch is exactly 2.54 centimeters, then we can convert our 7 feet into 2.1336 meters. All right, now we have force times distance. So, what does this equal? Well, the kilograms cancel. You'd think it'd be Newton meters. But no. It's not Newton meters. It's joules. Okay. So let's multiply this out. 2.1336, and we end up with 237.348 999.3 joules. And that's how they write it, just a capital J, and that's joules. Now I ask you, which system would you prefer? But he says the metric system is so simple. You got pounds, you got feet, you multiply them together, you got foot-pounds. Bam! You got kilograms? Oh, we got to change kilograms to newtons. So we have our gravitational constant of 9.81 newtons equals a kilogram, and that's only on Earth. On other planets, it's different. Then we have our force here times our distance, and you end up with some strange thing called joules. It's not even spelled like joules. Okay, so enough picking on the French. Let's get going here. Now, the next issue is, this is all well and good when the force stays the same. In other words, I'm picking up this weight, and this weight stays the same the entire path that it's being lifted. Now imagine if this weight had sand in it, and there was a hole in it. And so as I lifted it, the sand was seeping out. Now, how do you calculate work? Because you can't just go force times distance, because the force is constantly changing. This seems like a job for integration. Yes, integration. Okay, so we're going to start with the simplest type of problem and work our way to the juicier problems. Okay, so work is the integral from a to b of f of x dx, where f of x, oh wait, I'm sorry, I just messed something up there. Oh no, that's right. Okay. Yeah, right, because we have distance in there. Okay, so it's the integral from a to b of f of x dx, where f of x is the force at a given position x. So in other words, f varies with x. So the example I just gave you, I'm lifting a weight that the mass is seeping out of. Well, my force is changing continuously as I move it. So force is a function of position. Now, this is the work done between x equals a and x equals b, where x is the distance. All right, so simplest example, a particle is x feet from the origin. and it's acted on by this force, x squared plus 2x pounds. Notice, as x changes, the force changes. So we want the work moving this particle from x equals 1 to x equals 3. Well, so this is just a matter of plugging in the work definition. So work is going to be the integral from 1 foot to 3 foot of the force, which is x squared plus 2x. Now, remember I said work is force times distance? Where's the distance? It's right here, dx. See, dx is an infinitesimally small distance. So we're calculating this work over every tiny millimeter of distance. So there we have force times distance. Well, now it's time to crank it on out. So this is going to be x cubed over 3 plus x squared from 1 to 3, which equals 3 cubes, 27 over 3, which is 9, plus 3 squared, which is 9, minus, put the 1 in here, and we have 1/3 plus 1. So we end up with 18 minus 4/3, which is 16 2/3, or 49 thirds. And notice the force is pounds, the distance is feet. So we have good old American foot-pounds. That's it, game over. Okay, now, wait, something has gone awry. What did I do wrong? 9 plus 9 minus 4/3. So 18 minus 4/3, 16 and 2/3. Oh, 16 and 2/3, not 16 and 1/3. All right, I just made 16 and 1/3. So 16 and 2/3 would be 48 plus 2 is 50 thirds. Or, now see, this is physics too, so we would leave our final answer, work equals 16.67 foot-pounds. That's it. All right, now cruising onward. Now we have a little more practical example. You know, when you have a force that varies according to a function, that's all well and good, but it's not really practical. Here we have a practical example. We have a spring. Now, if you think about a spring, here's your basic spring. Now we have we'll put a weight on it. Now, there's a natural length of the spring. Now, if I pull it, it's going to be creating force against my pulling. And the further I pull it, the harder it gets to pull. Now, it goes back to the natural position. Now, if I were to push it, the same thing's going to happen. As I'm pushing, at first it's easy to push, but then the further I push, the harder it gets. So the force changes as the weight is moved. So that's the interesting thing about the spring, is that it's a practical example of where force changes with distance. So our spring, we find out that 40 newtons is required to stretch it from its natural length of 10 centimeters to 15 centimeters. So if its natural length is 10 centimeters, I'm moving it 5 centimeters with 40 newtons. Okay, now, we want to know the work that it's going to take to go from that 15 centimeter point up to 18 centimeters. So, first thing we do is we need to get the spring constant. And the spring constant is force that will keep it in red. So force equals kx, where k is the spring constant. Well, they gave us 40 newtons equals k times, now we went from 10 to 15 centimeters. That means we moved it 5 centimeters. Well, we're in France. We can't just stick with centimeters. We have to change it to meters because newtons, meters, kilograms all fit together. So the 5 centimeters that we moved it to get from 10 to 15 centimeters actually equals 0.05 meters. Okay, so we have to put 0.05 meters in here. And now we can solve for k, which equals 40 over 0.05, and that's newtons, and you have to kind of say that with a little nasal quality, newtons per meter, which is 40 divided by 0.05 becomes 800 newtons per meter. And we're just going to leave it 800. It's a spring constant. All right, now we're trying to find out the work. Well, work equals force times distance. And remember, the distance is our dx because it's going to be changing. The force will be changing every infinitesimally small distance. So our work in moving it from 15 to 18 centimeters is going to be the integral from 0.15 to 0.18 meters, so distance in meters, times force, which equals kx. Well, let's put that down here. So we just found out that force equals kx, so that means force equals 800x. So that's what we're going to put in here, is work equals force times distance. This is it. Now, once you have the integral set up, it really becomes easy, but this is how you set it up. The work going from 15 to 18 centimeters, don't forget to change that to meters, and then force, which is 800x, times distance. And remember, force is just kx. That's how you get that. So now we just go to town with it. So we have integral, oops, no, we don't need integral. We can evaluate the integral now. So we've got 800x squared over 2, which is 400x squared, from 0.15 to 0.18. And that equals 1, oh no, I screwed up. It's not 0.15 to 0.18. It is the distance from the natural length. So the natural length is 10 centimeters. Now we're going from 15 to 18, so that means we're really going from 5 centimeters away to 8 centimeters away from the natural. Okay, so 10 centimeters is the natural length of the spring. Well, we're not counting those 10 centimeters because the spring is at rest. It takes no force to get there. So we're really starting at 15 centimeters is 5 centimeters past the natural. And so if we were going from 10 centimeters to 18, then the 10 centimeters would be at 0. So it's 5 centimeters past the natural to 18 centimeters past the natural. Yeah, to 8 centimeters past natural. So it's 0.05 to 0.08. Okay, now we're back in business. I knew something didn't look right. So 400 times 0.08 squared is 0.0064, and 0.05 squared is 0.0025, and you subtract that, multiply by 400, you get 1.56. What are the units? It's work in France, joules. 1.56 joules. Okay, so recapping the action, F equals kx. All you do is plug in your force, plug in your distance that force got you, and you can solve for the spring constant. Once you know the spring constant, then you know F equals that number times x. So there's your force. Now the work is going to be the integral from the distance from the natural length to the final distance from the natural length in meters. And then do your integration and you get your work in joules. That's it, game over. Okay, now, next we're going to crank up the juice just a little higher. We've got a 200-pound cable that's hanging off a building. It's 100 foot long, and we're trying to find the work to get it on the roof. Now, if you think about this, here's my building, and here's my cable, my red cable, that's hanging off the building. Okay, now, this is 100 feet from here to here. Now, you're the guy up on the roof that is asked to lift this cable up onto the roof. Now, if you think about it, the first foot, well actually the first infinitesimally small distance you pull it, you're pulling the entire 200 pounds of the cable. But once you pull some up there, it's resting on the roof, and you're taking another pull. You're not pulling the whole 100 feet. You're only pulling what's left. So it's not as heavy. So if you think about it cranking a pulley, then that first little bit, you're lifting the entire cable, but then as you crank, you're lifting less and less. And think about the last foot. Well, the last foot's only 2 pounds worth. So your weight of your cable is decreasing as you lift the cable. So, and notice this cable in the good old USA. It's 100 feet long and it weighs 200 pounds, and that makes it nice. So, there's 2 ways that you can think about it. If we make 0 at the top and 100 at the bottom, then our work is going to be the integral from 70, take 2. The integral from 0 to 100 of the force. Well, the force is 200 pounds, but it's 200 pounds in 100 feet. So that basically makes it 2 pounds per foot. So the force is going to be 2 pounds per foot, which is 2x, where x is in feet. And then each increment is going to be a dx. So there's force times distance. So now this is going to end up being the, it's x squared from 0 to 100, which is 100 squared, which is 10,000. What are the units? Foot-pounds. Easy. Okay, now, I want to show you a different method that you could do, and that would be if we let the 0 be down here and the 100 is up here. Okay, now, in this case, we would be going the integral from 0 to 100. Not 2x, but 2 times 100 minus x. Notice the distance that we're pulling. Well, x is really whatever distance along the way it is. But if we're saying the top is 100, then any distance that we've pulled it is going to be 100 minus x. Now, I kind of like that better because it makes a little more sense when you're not pulling the entire cable up. So now this is going to end up being 200 minus 2x. So when we do the integration, it's going to be 200x minus x squared from 0 to 100. And now when we put our 100 in here, it's 20,000 minus 10,000, which equals 10,000 foot-pounds. Same answer. Now, let's do a little variation here so that you can see the difference in the two systems. Let's say we don't want to pull the entire cable up there. We only want to pull 30 feet of it. Okay, now we're going to do the red method and the blue method. So if I do the red method, this is where the red method is going to be a little confusing to some people. Okay, I know that my force is still 2x, and my distance is going to be dx's. But if I'm only pulling 30 feet of it, well, when I'm finished, there will be 70 feet left hanging over the top. So remember, we said 0 is up here and 100 is down here. So really, we're going from 70 to 100 feet. If we only want 30 feet up there, it's the integral from 70 to 100. If I wanted 60 feet, then it'd be the integral from 40 to 100. Remember, 100 is the bottom of it. So you're going from top to bottom. From top to bottom is 70 to 100. It's going from 70 feet, or it's going from 100 feet hanging over to 70 feet hanging over. Now, let's do this integration. So this is going to be x squared from 70 to 100, and that's going to be 100 squared is 10,000 minus 70 squared, which is 4,900, and so that's going to equal 5,100 foot-pounds. Now, think about this. If you're pulling the entire cable up, and the entire cable takes 10,000 foot-pounds to pull, if you're pulling 30 feet of it, you're pulling 30 of the toughest feet, because you're pulling the entire cable initially and you're leaving 70 feet. So the work is more than half of what it would take to get the whole cable up, because the work from the other 70 feet of cable is going to be less because it's way lighter. All right, now, let's do the blue method. And the blue method, if we're doing the first 30 feet, is just the integral from 0 to 30. See, that's why I like this method a little bit better, because it's a little more intuitive if you're not doing the entire cable. Now, watch the magic. So we have integral from 0 to 30 of 200 minus 2x. And so this is going to be 200x minus x squared from 0 to 30. Well, here your integral's easier too now. So you plug in the 30, 200 times 30 is 6,000, minus 30 squared, which is 900, and you end up with 5,100 foot-pounds again. So, you can choose which way you like, but I kind of think this keeps you out of trouble. So instead of just 2x, it's 2 times 100 minus x. And then if I want any fraction of the cable, then I'm going from 0 to whatever amount of cable I want up there. Whereas if I want some fraction of the cable here, I'm always going to 100 at the top, and how much ever I want to pull up is going to be the difference from 100. So either way works. All right, now, we're about to crank it up to maximum juice. Maximum juice! Okay, so we've got a conical tank filled with a fluid, which we'll just say it's water. So we want to find the work required to pump the tank up. Now, a lot of people, without thinking very much about it, think that that work is going to be, well, the force of pumping the tank will be consistent all the way through. Think about this. When you have a drink, like you have a 24-ounce cup of Coca-Cola, and you have a straw in it, so you're basically pumping out the cup, you're sucking out the cup. Is it more difficult to suck at the very beginning or at the very end? So when there's like 1 inch left, is it more difficult to suck than when the entire cup is filled to the brim? Think about that. It's more difficult as the drink gets lower. Because when you first start, you're really only lifting the water from the very top of the cup up to your mouth, which is only a few inches. But when you're getting the bottom part of the liquid, you have to lift that liquid all the way from the bottom of the cup up to your mouth, which is almost a foot by then. So, so the work required to pull liquid out of the tank gets greater as the tank gets lower. Now you might say, well, I had my straw at the bottom of the cup, so why would it be more work at the end? Because I'm still pulling the fluid all the way up from the bottom, even when the drink is full. Well, you are, but you also have the weight of the fluid that's pressing down on the fluid at the bottom. So it's actually being pushed up the straw all the way till the top of the drink. So now, one more thing. It's the exact same work required to pull water up from the top of the tank as it would be to pull it off the bottom and then pump it up. So in other words, it's the same work to suck it as it is to push it. So that's, now let's get on this. So the work is still force times distance. The distance changes and the force changes. So first of all, we've got a 10-meter tall cone that's 4 meters in diameter. And it's filled to 8 meters. So we're really pulling it from 8 meters high down to the bottom. So now, I would advise that you think of this as top to bottom. In other words, we're pumping from 2 meters below the top. Come. There we are. 2 meters below the top to 10 meters below the top. That's the way you should think about it, is you're going from top to bottom. 2 meters below to 10 meters below. Now, any given layer is going to be a certain radius and a certain depth below the top. So really, we're looking at this fluid as layers of fluid because each layer weighs a different amount. So, we'll say each layer has radius r and depth x below the top. So I probably shouldn't call it depth. I should probably call it distance x below the top. Yeah, let's do that just so people aren't confused. Now, we can make a pair of similar triangles out of this relationship. Here's our triangle, and we've got 8 here, and we've got the entire thing is 10. And then we've got 2 up here, and we've got, oh, I'm sorry, we don't want to call that 8. It's 8 when it's full, but it's 10 minus x. Remember, x is the distance below the top. So now, 4 is the diameter, so 2 is the radius. And so, I'm just going to call this radius r. So, what we can say is, blue radius to blue depth, r over 10 minus x, equals 2 over 10. See, what I'm saying is the horizontal to the vertical equals horizontal to the vertical. So now if I cross multiply this, I get 10r equals 20 minus 2x. And when I divide by what did I just do wrong? 20 minus 2x. Okay, now I'm going to divide by something has seemed to go awry. 4 over 10. Oh, yeah, okay. I copied the problem wrong. That's why. Okay, this is not 4 meters from here to here. It's 4 meters from here to here. So the radius actually is 4 meters. I was thinking they were telling us the diameter was 4. All right. So the radius is 4. So that makes our fraction here, yeah, let's get rid of all this. That makes our fraction 4 over 10 equals r over 10 minus x. Okay, so now when we cross multiply, we get 10r equals 40 minus 4x. And that means r equals 4 minus 4/10 x. Okay, so that's my radius at any position. See, as the water level goes down, the radius also goes down. So now I know then volume equals pi r squared times delta x. And that's going to be the volume of any given slice of water. See, I'm calling this a slice of water because remember, we're thinking of this as infinitesimally small slices that we're adding up. So the volume of any given slice is pi r squared delta x. And you know that delta x is going to be a dx when we integrate because it's infinitesimally small. So this is going to equal pi times r, which I just said was 4 minus 0.4x squared. So there's pi r squared delta x. Now, next thing we know is density equals mass divided by volume. So that means mass equals density times volume. So that means our mass equals the density of the water, which is 1,000. Well, let's do it over here. So mass equals 1,000 kilograms per liter. Well, let's just put this here. Mass of water is 1,000 kilograms per liter times the volume, which would be a certain liters. So notice the liters cancel, you're left with kilograms, that's mass. So we have 1,000 times pi times 4 minus 0.4x, 20 squared, times the delta x. So that's our mass of a slice of water. Now, force, remember this is in France. So this is mass, that means we're in kilograms right now. Well, we can't use kilograms, remember we need newtons. So how do we get newtons? We need to multiply by 9.8. So force equals mass times gravity, which equals kilograms times newtons per kilogram. So your force ends up being in newtons. All right, so we have a force then of 9